Okay, so this is part 2 of our introduction to pseudospectral methods. And here we'll talk about Fourier pseudospectral methods, where our function u on the grid, so uj is a linear combination of basis functions where the basis functions are Fourier modes. This e to the 2 pi inx over L is equal to cosine of 2 pi nx over L plus I sine of 2 pi nx over L. So those are periodic functions. And that means that we want to, we're going to apply this to PDEs that have periodic boundary conditions so that U is consistent with that. So we're going to make a grid of uniformly spaced points. So our domain is L, and our grid X goes from 0 to L. The function U of X is periodic with period L. And our grid, suppose we have big N is 6 grid points, then our grid points would be index j is 0, 1, 2, 3, 4, 5. And we're periodic on big L. And notice that big L spans to this next point that with an open circle. That's not part of our grid because this point happens to be the same as point j is 0 due to the periodicity. So you could imagine this grid being wrapped around a circle, and if we did that, then this open circle would overlap with point j is 0, and so that's why it's not included. So sometimes you'll see this grid written with the open circle first, and then we'd fill in this last point, and that's just a matter of preference on which one you use. So we have sines and cosines, and we want to know how they fit on this grid. So if we look at cosine of 2 pi nx over L, then when n is 1, x is going to range from 0 to L, and when it's 0, cosine of 0 is 1, and when x is L and n is 1, we have cosine of 2 pi, which is also 1, and we end up with a single period. So we go from 1 up here to 1, and that would happen on the whole domain. So we go from 0, we go from 1, and a single period would land us at the other end. If we increase n and make it 2, then we get to 2 pi twice as fast, and so we get a wavelength here, and then another wavelength there, all as x goes from 0 to L. And if n is 3, then we would have 3 periods, 1, 2, 3. And it turns out that the maximum number of periods that you can fit on a domain with n grid points is equal to n over 2, big N over 2. And you can see that here. So we go from 1 to minus 1 to 1 to minus 1, 1 to minus 1. That's as much as you can fit on a grid as we go from 1 to minus 1, etc. on subsequent points. So we call this the Nyquist limit, and the maximum n max is equal to big N over 2. And when we insert that in here, we get cosine pi n x over L. And that's basically plotted here for big N is 6. We've also plotted the same thing for sine. So if we plot all the cosine and sine waves together, on the left we have cosine 2 pi nx over L for n goes from 0 to n over 2, and the same for sine. So when n is 0, we have cosine of 0 is always 1, this blue curve. When n is 0, sine of 0 is always 0, so the blue curve is here. And then when n is 1, we have a single full wave on the domain. When n is 2, we have 2 full waves on the domain, this green curve. When n is 3, we have this red curve, 1, 2, 3, and the same thing for the sine. Okay, so we're combining sine and cosine waves, and if we do that, then we can write this as a0, which is just a constant offset, plus an cosine and bn sine of this argument here, and we said that we can go from 1 to n over 2. Well, we went from 0 to n over 2, but we've already accounted for the 0 right there. So let's relate this to the Fourier mode, the complex Fourier mode. And we're going to do that as follows. So you might want to pause the video, take whatever time you need to fully and completely absorb this slide. But here we've written this, Euler's identity is e to the I theta is cosine theta plus I sine theta, and we've multiplied across by r. So we have the polar coordinates, r e to the I theta listed here, and then the Cartesian coordinates would be this point, r cosine theta drops us down to the x location on the real axis, and r sine theta drops us over here to point y on the imaginary axis. Now we can relate these further. We're going to take this equation here and relate it to the Fourier modes, e to the 2 pi nx over L, and we can do that using the Euler identity. Again, e to the I theta is cosine theta plus I sine theta, and we can write cosine theta equals 1/2 e to the I theta plus e to the minus I theta, and we've done this so that the imaginary parts cancel. We can do the same thing for sine, writing e to the I theta minus e to the minus I theta, and then this has an imaginary term that we cancel with the 1 over I, and again the 1/2 term. So these are easy to verify. You can pause the video and convince yourself that these identities work using these three equations. And if you insert these two into this equation, then we get the following. Here we have a summation over the cosines and we have a summation over we end up with two summations here. The first summation has this Cn e to the 2 pi I n x over L, Kn e to the minus 2 pi I n x over L. That just arises because we had plus and minus terms here. Now, of course, when we do the substitution, we're substituting this whole quantity 2 pi nx over L in for theta. Now, what we want to do is make a single summation out of this, because remember, we're trying to get to this thing with the single summation and these e to the 2 pi I n x over L with just the positive component, not this negative component. So let's see how we can do that. First of all, we've defined coefficient Cn as shown here, and coefficient Kn as shown here. So this relates these coefficients back to the coefficients of the cosine and the sine. Now, we want to make this a single sum, but we can't do that because the sums are over the same n, but they've got different signs for the exponentials, so we can't do it. But if we replace n with minus n, just combine the minus n here and just call that n, then we can do that as long as, but it makes this sum go from minus n over 2 up to 1. So that's kind of cool. If you just change this minus n to n, then it works fine as long as your summation goes from minus n over 2 up to 1. And oh, sorry, not for 1. It's minus 1 to minus n over 2. The point is that when you do that, this sum is over a different range than this sum. And these exponentials are the same, but these are over different sums, so we can combine them and just replace Cn with Kn. Okay, so let's do that. Also, we're going to incorporate a 0. So when n is equal to 0, this exponential term is just 1, so we can just fold a 0 into this new sum term, and we get the following. So we go from n is minus n over 2 to n over 2, Cn e to the 2 pi I n x over L, And we got to be careful with our CNs here. So being careful with what we did, we have Cn is A0 when n is 0, Cn is an over 2 plus bn I over 2 for negative n, and as shown for positive n. So great. So this is now, we've got the equation that we want, and we've related the coefficients to the coefficients of the sines and cosines on our domain. Okay. Now let's stop for just a minute or change gears a little bit and just look at this e to the 2 pi I n x over L. So that thing is a point on the unit circle in the complex plane. So each one of these sums is a complex coefficient times a point on this unit circle. So we can write this as e to the theta sub x n I, where theta sub x is 2 pi x over L. It's convenient just because we have this angle theta. And then we're going to have n is going to go positive and negative. So we're going to have positive values. We're going to have n is 0. N is 0 is part of the sum. So we have 0, 1, 2, 3. So if big N is 6, we have we're going to go to 3, n to minus 3. So we go 1, 2, 3, and we go the other way. 1, 2, and minus 3 are our angles. So these points have conjugate symmetry, and conjugate symmetry means that the real parts are the same, but the imaginary parts are the same except they have opposite signs. So when we go the positive direction, we go up 1 here, and when we go negative, we go down 1 here, and they have the same real part on the x-axis, but they have opposite imaginary parts. And so we've connected those with this dashed gray line to illustrate that. Okay, now what we're showing here is when x is delta x, we have e to the 2 pi I n over n, where delta x over L is equal to 1 over n. So we've changed this 2 pi x over L to 2 pi n over big N when x is just a single delta x. And then this n varies as we've shown as we step around that circle. So let's look at this in some more detail. So the figure represents these basis functions for x is delta x. Now we don't just have x is delta x, we have the basis functions at other x's. And in general, our other grid points are xj is j times delta x. So if we look back at our grid, we have 1 delta x, 2 delta x's, 3 delta x's, 4 delta x's, 5 delta x's, 6 delta x's. And when we substitute these in, xj is j delta x, and delta x is L over n. Then if we substitute this in, then we get e to the 2 pi I n j over n. So when j is 1, we step around plus and minus, clockwise and counterclockwise, as shown. But for other j values, when j is 2, we're going to step twice as big. Each step will have twice as big of an angle. And when j is 3, each step will have an angle 3 times as big. And when j is 4, 4 times as big, etc. So let's show this in the following figure. When j is 0, j is 0, it's e to the 0 is just 1, and all the n's, for every n, it's just always e to the 0 is 1. So point n is 0, n is 1, n is 2, n is 3, n is minus 3, minus 2, minus 1. They all just sit at this point. When j is 1, we have the situation on the previous figure. The red curve indicates the angle that we're stepping for each n. So you'd go we go n is 0, step to n is 1, step to n is 2, step to n is 3, 0, step to n is minus 1, step to n is minus 2, step to n is minus 3. Now when j is 2, we take twice as big a step, so our basis function is a little wider. And now we go 0, 1, 2, 3, and now the negative direction, 0, minus 1, minus 2, minus 3. When j is 3, we go 3 of these, 1, 2, 3, and we go 1, 2, 3. And then we go the negative direction, 1, 2, 3. And then when j is 4, it's even bigger, so we go 1, 2, 3. And then the negative, we go minus 1, minus 2, minus 3, and similarly for j is 5. Okay. Okay, so we've mentioned that for real scalars u of x, the Cn have to have conjugate symmetry, and that means that the imaginary parts of the sum cancel. So remember, we're summing up terms here that look like a complex coefficient times a complex, this is also a complex number. And we want the imaginary term to cancel, because if u is real, we need the resulting sum to be real. So let's look at, we've said that C has to have conjugate symmetry so that it will cancel. Let's verify that. We already know that the Fourier modes have conjugate symmetry. As we step around the circle, all the points of the E do. But now let's look at what happens. We'll show that the Cn also have to have conjugate symmetry, so that when they multiply this Fourier mode, the whole term, the whole imaginary part cancels. So you can read through these. I'll talk you through it, but you can skip over it if you don't want to see the details. But let's consider two terms of the summation on opposite sides here. So when we have 1 and minus 1, or 2 and minus 2. So if we have Cn and C minus n, then we have the real part and the imaginary part, and we have the real part and the imaginary part. So when we sum each of these times their corresponding Fourier mode, e to the 2 pi I n x over L and minus 2 pi I n x over L, when we expand these and cosines and sines, we get this. If we collect the imaginary parts, we have this. And because the sine function is odd and the cosine function is even, the imaginary parts will cancel if Cn real is equal to C minus n real. So again, because these because of this odd behavior, we can replace this minus out here, and then these two terms will cancel if CNR equals C minus NR. And then similarly, if CNI equals minus C minus NI. And this is just another way of saying that we have conjugate symmetry. So you can show that on a term-by-term basis, which is great. You can also use the conjugate symmetry as verification of the model and take advantage of that as needed. It's also a way to not be scared away by complex numbers, because our function is real and it stays real throughout. Okay, now we've been summing from minus n over 2 to n over 2, but you'll notice in all these pictures the 3 and the minus 3 overlap, and the 3 and the minus 3 overlap, and the 3 and the minus 3 overlap. They always overlap, which means you have 2 points at the same place. And that's redundant. And so we can get rid of that effectively by removing one of the two endpoints. And we remove the endpoint minus n over 2, and so our sum goes from minus n over 2 plus 1 to n over 2, and we get this function right here. Okay, we put it in blue because it's special. Now we've been considering even values of n. For odd values of n, the smallest period is still 2 delta x, which is 2L over n, but the max number n of these waves that fit on the grid is this floor function, so we round down. So if n is 5, we have 2.5, but we round down to say, okay, we don't get 2.5, we only get 2. So for n is 5, we would go from minus 2, minus 1, 0, 1, 2. And for x is delta x here, n is 6, and n is 5, we have the points as shown. We still have the conjugate symmetry, but you'll notice that pi is no longer included. So that's fine. Just keep those little details in mind as you think, well, we've got n over 2, we have these are integer n's, what are we going to do? You just take the floor. Okay. And that's where we'll stop.